All right, good morning, good afternoon, ladies and gentlemen. Welcome to this series of online lessons. If you haven't already, please subscribe to the channel and leave a like for this video. Now, in today's lesson, we are looking at question number 3 here, which focuses on linear independence and linear dependence. Now, in today's lesson, particularly, we are going to look at linear independence and maybe define linear dependence. And today I am with my live class. I am with Mr. Mundopu, so we can start. Hello, Mr. Mundopu, are you able to get me?
Yes, I can.
All right. So we can start, right?
Yes, you can.
This question focuses on linear independence and linear dependence. All right, so the definition of linear independence. So we've been told that this is linearly independent, right?
Yes.
Yes. So now if something is linearly independent, so if these two are linearly independent, then we can write them as a linear combination. That is alpha 1 times u plus alpha 2 times v plus alpha 3 times w. This will be the linear combination, and all the scalars alpha 1 will be equals to alpha 2 will be equals to alpha 3, and all these scalars will be equal to 0 if u comma v comma w are linearly independent. Okay, so this is the definition of linear independence. So if you have they can even be infinitely many vectors. So for instance, if you have a vector which has this set 1, or let's say alpha 1 or u1 comma u2 comma u3 all the way to un. So first of all, we need to write these as a linear combination. So that is alpha 1 u1 plus. All right. So we're saying
Can you see the screen?
all right, just a minute. All right, so we are saying if we are given a set of vectors like this, first of all, if we can write it as a linear combination like this, all the way to alpha n un equals to 0, and if we can find all the scalars, alpha 1, and these scalars are all equal to 0, alpha 2, they are all equal to 0 all the way to alpha n. So if all of these scalars are equal to 0, then we conclude that they are what? They are linearly independent. The vectors in the set are linearly independent. So that is the definition of linear independent. So for this question, we have been told that these three vectors, u, v, and w, are linearly independent. Okay, so meaning that first of all, they have a linear combination and all the scalars are equal to 0. In other words, we can even write this as u 0 plus v plus 0v plus 0w equals to 0. So since these vectors here are linearly independent, now we've been asked to show that this set will also be linearly independent. So for us to show that this set will also be linearly independent, first of all, we should write this set as a linear combination. Okay, and writing it as a linear combination, we'll just multiply the scalars with the vectors here. So we'll say this is the first entry, so it will be alpha 1, or let's use different vectors. Let's use beta. So it'll be beta 1 u, okay, plus we multiply the second entry plus beta 2 u plus v,
Open bracket, u plus v,
plus beta 3 u plus v plus w, and this should give you what? 0. So now here our issue is to show that this is also linearly independent. So if u comma u plus v comma u plus v plus w is linearly independent, then beta 1 should be equal to beta 2 and should be equal to beta 3, and they all should be equal to what? 0. So our thing here is we just need to show that beta 1, beta 2 and beta 3 are equal to 0. So first of all, let's expand this and group those with u's alone and those with v's alone. So here when we multiply this to just be beta 1 u plus, when we multiply this, that will be beta 2 u plus beta 2 v. When you distribute here, we're going to have plus beta 3 u plus beta 3 v plus beta 4 w. This should be equal to 0. So we group those with the u's alone. So these are those with the u's, and those with the v's alone. So this would be beta 1 u plus beta 2 u plus beta 3 u plus
beta 1 u plus
beta what?
beta 2 v, 2 v plus beta 3 v plus the beta 3 w equals to 0.
Oh, should be 3, right? Not 4.
Yeah, you have written 4. It's supposed to be 4. 3.
Yeah, thank you very much. So it's supposed to be 3 here. Okay, so since we are distributing this beta times that, beta 3, this beta times that, that's beta, and this beta times that, that will be beta 3. Thank you. So beta 3 w equals to 0. Okay, so now here we can factor out the u, so it will be beta 1 plus beta 2, the u outside. Then here, what is it like that? When we factor out the u here, what are we going to have?
No, beta 1, beta 2, beta 3.
Okay.
Then you outside.
Okay, then plus here. Here, what are we going to have?
We are going to have beta 2, beta 3 plus beta 3, a close brackets, then our v outside.
Okay, then here.
Then we are going to have beta 3 w.
Okay, now here, remember, we said but alpha u plus, that is alpha 1 plus alpha 2 v plus alpha 3 w equals to 0 is linearly independent.
Yes.
Okay, remember that. So we've established that from the question. Say alpha 1 u plus alpha 2, this is linearly independent, meaning that what are the values of alphas here? the values of alpha here, this is 0, u.
So since we are doing now, they were 0.
Yeah, so 0 v
0 v plus 0 w
is equals to 0. So now here we'll equate these to these. Are you seeing that? Since there is u here and there is u here, so we equate this to this, we equate this to this, okay, and this to that. So after we equate that, we're going to have beta 1. Let me write the colors for beta 1. So we're going to have beta 1 plus beta 2 plus beta 3 equal to 0, since these are linearly independent, so equal to 0. Same applies to this. It will be beta 2 plus beta 3 will also be equal to 0, because here and this are the same. Then here we're going to have beta 3 also equal to 0. Now we can solve. So beta 3 is already equal to 0, so beta 3 is equal to 0. So we can find beta 2 from beta 3. So we say beta 2 plus beta 3, which is just 0, will be equal to 0, meaning that beta 2 is equal to 0. Then here we can find beta 1 from beta 2 and beta 3. So we use this one, beta 1 plus beta 2 plus beta 3 is equal to 0, and that beta 1 plus 0 is equal to 0, and beta 1 will be equal to 0. Okay, so now remember what we wrote here. We said if this set is linearly independent, then beta 1, beta 2, beta 3 should also be equal to what? To 0. And basically here, since we've found that beta 1 is equal to beta 2 is equals to beta 3, and they are all equal to 0, we can conclude that if, we can say therefore, if u comma v comma w are linearly independent, then u comma v plus u comma u plus v plus w is also linearly independent. Okay, so that is the conclusion that we can make here. Okay, and the idea, just to run you through the idea, so the idea was here, if u, which is this, is linearly independent, so by linear independence it just means when you write the linear combination of u, v and w, you're going to get alphas that will be equal to 0, and basically the coefficients of u, v and w are 0. So now we come to this. So since it's the same u and v, we come to this, we are going to find the linear combination of this, which we did here. So b beta 1 u plus beta 2 u plus v, and so on and so forth. Then here we make a conclusion to say if these u plus v plus w is linearly independent, then also the coefficients, which are these coefficients of these, they should also be zeros. Okay, now how are we going to find these zeros? So we expanded this, which we had this, Then from here we grouped the like terms. So after grouping the like terms, we factored out the u's, the v's, and this one to find beta 1, beta 2, beta 3. Then we equate, since this u is the same u in the previous question, which was alpha u plus and so on and so forth. So we equate the coefficient. So this coefficient will go with the coefficient there. This coefficient will go with the coefficient there. And this coefficient will go with the coefficient down there. Is there. Okay. So now we equate. So this coefficient equated to 0 will give us that. And we solve for beta 1, beta 2, and beta 3, and we get and find that they are all equal to 0. And since they are all equal to 0, we conclude that this set is linearly independent. So this is how you're supposed to work this one out.